Hello, my name is Rez, and I'm a professional game programmer, and I do electrical engineering as a hobby. And today was an interesting day for our technical video on day 12. We're switching off this light, so I want to talk about a few things here. I want to talk about this circuit where a couple days ago I was like, well, why are we building this circuit? And it's funny, I didn't even make the connection of the Darlington Pair here, but that's probably what they're trying to do, even though I don't think it's necessarily the right thing. As I showed in that video, I got a better overall amplification from not doing this, from doing the common collector amplifier that I built on that day. But coming here, this is the better choice because now we have two transistors that are working together. When I talked about this before, I talked about this transistor man, and this, again comes from the art of electronics. But I talked about this transistor man who is basically changing the overall impedance as he sees this incoming current. And that's what's happening here as well. We're changing this overall impedance. This is dropping, and it does it based on this HFE thing or beta. It's called either of those things. I usually see it written as beta, but either is perfectly valid. Now, a Darlington pair looks like this. Not that. It looks like this. This is just the classic schematic for a Darlington transistor configuration. You have two transistors. Typically, they are the same transistor. At least I've usually seen them as the same transistor. And you can see the formula where the beta of this Darlington pair equals the product of the beta of the other two. So it gives us a much higher gain. It allows us to take two lesser transistors. It splits the heat generally between them. It's generally a pretty good, nice setup. There are a few issues with it. One example is that normally you have a sort of base emitter voltage drop, and you have to account for that. And that voltage drop is usually around 0.7. But both of these, now this sort of base emitter junction of this pair, because we can think of these two transistors as a single unit with a single base coming into Q1, a single emitter out of Q2, and a collector where they're both tied collectively. We can see this whole thing as essentially a single transistor. And the base to emitter, you double that voltage drop. So you just have to deal with that kind of thing. Okay, so this is just the schematic. I've just redrawn it here so that I can draw all over it. We have our 10K resistor here. We have our 470 here, our 4.5 supply right here. So this is just that exact same schematic. Here's our Darlington pair over here. So let's talk about how this actually works. And I'm going to talk about it in two different ways. We're going to start with the on set. I'm going to draw that in this green pen. So in the on scenario, there is no light that's getting to this thing. That means that this thing will have approximately infinite, if I can draw this infinity symbol, infinite ohms, right? This is going to be like an open switch. It's as if this whole thing is out of the circuit. That's probably the best way to think about it. Because nothing or very little is going to be coming through here. So it's as if it's as if I pulled this component out and it's an open wire. So it's going to be conducting this way. We're going to be drawing current like that. Up here, we have our rail, our positive rail. This is plus 4.5 volts. Down here, we have our ground, which is our 0 volt reference right there. And so what that means is if we I'm going to assume very basically, I'd have to look up the data sheet, but I think it's about 0.7 is going to be dropped between both of these guys. So we have 0.7, 0.7. So this whole thing is about 1.4 volts. So if we do the math and we take 4.5 minus 1.4 dropped from these two junctions, we have about 3.1. If we divide that by 10,000, which is this guy, this is the only sort of linear component in this leg of the circuit, this is going to be 310 microamps. So we get a very small amount of current. That gets multiplied by the beta of this thing. Now the beta is not small. when I looked at the data sheet, it was somewhere, if I recall, it was somewhere between 100 and 160. It just depends. And remember, these are multiplied together. They're not added together with these two transistors. They're multiplied together. So let's just go with 100. 100 times 100, as you know, is going to be 10,000. So we have an approximate beta equals approximately 10,000. So does that mean that we're going to have, what did I say, 0.00031 times, 10,000? Are we going to have 3.1 amps? No. We could draw 3.1. I mean, burn out those transistors for sure, but we could technically try and pull that. But of course, remember that this motor, that's the current going through the collector section. That would be the current going through here. This motor has a say. What it does mean is it means the motor is going to conduct as much as it can. And this voltage here dropping across this transistor, it's going to lose, it's going to be approximately 0 volts from here to here. Approximately. It'll drop something. So we're going to get a decent amount coming through here. It's going to be in solid conductive. It's going to be almost as fast as if we had just directly hooked the wires up to it. So that's what happens in the on stage. In the off stage, which I'll draw in red, things get a little different. What happens is we do have light here. So we have light shining here. What does that do with this guy? It basically turns it into, it's not exactly a short, but we can say that it's approximately 0 ohms. What this is going to do is it's going to act, think of it like a short. So now, let's say that you are a bunch of electrons, right? You're these electrons hanging out here in the negative side of the battery over here, and you've got some choices to make. Like you're going to go down this path, but you've got some choices to make, right? You can either go through this, NP these two. We have two PN junctions here. You can go through these, or you can just skip all that and just go through this essentially a short. So as long as the resistance here as long as it's better to go through here than to drop this 1.4 here, then it's just going to short this out, and these transistors will not conduct. They'll essentially be an open switch, and you'll be here. So that's what's going to happen. That's why this is happening. And we can watch it happen. So I've set up this meter to basically measure the voltage drop across the photo transistor. If I just turn this on, we can see that the voltage drop here is about 1.3. Now, I would expect that it's actually measuring this. I said it would be about 1.4. It's measuring this approximately 1.4 because I'm measuring from this point to this point, so it's seeing this drop here. And I'm seeing 1.3-ish. That's about what I'd expect. Especially if I try and cover this up. Now, if I do this, we can watch it just plummet, right? This says 52. It says millivolts. There's a little M there. So we're at nothing here. If I'm here, this is nothing. I mean, this is very, very, very little. So we can see that change. Now, this meter on the right, I just have hooked up to these probes. So we'll just probe around. This is the on stage. So we're dropping from this resistor here. See if I can get a good connection. There we go. We're dropping about 3 volts. So my math was approximately correct here. I would expect 3 volts over 10,000. I should have about 300 microamps going through that. It's a Darlington pair, so a tiny little bit of current is all that's necessary in order for us to be able to have these transistors in conduct mode. Okay, let's measure across the collector. That's going to be from here, the negative side of the motor, or the collector pin down here. All right, and I've got this here. This is in the conduct mode. I have to create a little shadow here. So that collector to ground is giving me about 0.8 volts, and that's about right. Looking at the data sheet, in full conduct mode, you expect the emitter to collector junction to be about 0.8. And that's just from the data sheet from 2 or 3 days ago when we looked at it. Now, if I put it into full conduct mode, into full open mode like this, now it's dropping the full 4.5 volts. It's dropping basically everything here. It's fluctuating there because I'm moving my hand. I'm trying to keep the LED in like I have this precarious thing going on with my hands. So there we go. Yeah, so it's dropping 4.5, and you'll note that we're dropping 80 millivolts from this phototransistor. So that's going to give us, essentially a short there. It doesn't have enough pressure, it doesn't have enough voltage to push through the two PN junctions that are there. And if I raise this just a little bit more, it's hard to get it exact. There it goes, it's conducting. There, I'm at about 1 volt and it's not conducting, right? Not conducting. There, it has to break that 1.4 volt barrier. Once it does, it conducts. And that's it. That's today's fun little lesson about the magic of Darlington pairs, basically having transistors work in concert here like this. And as I said in the other video, I suspect we're going to have multiples of these circuits. So I will see you all tomorrow.